Hello, welcome back to the Chemical Equilibrium series. Now we're going to look at more interpretation of equilibrium constants. I think it's important to note that equilibrium is also called the law of mass action. So this is the same thing. If you hear this, means this, hear this, means that. And so I think it's also important to note, because I did not in the other one, that kind of the overall symbol for this whole thing is KEQ. So the KEQ is kind of your big category, and under KEQ you have several different types of equilibrium constant expressions. In the case of this one you have Kc, and we talked about Kc as being expression of concentration, and then we also talked about in the last one about what Kp was as far as the concentration of partial pressures, or the partial pressure constant. And so we also talked about how those are interrelated to each other. Now, I also alluded to in the last one that because the Kc is the concentration of the products divided by the concentration of the reactants, if the products are large, you're going to have a big number in the numerator and a small number in the denominator, and therefore your resulting answer will be a big number. So you see this is 5.0 times 10 to the 12th is a very large number. And so what that tells us is that this reaction mostly becomes the product, and very little of the reactants will be left. There'll be some, but very little. And so what we call this kind of reaction is a lie to the right reaction. And the reason why we call it that is because in terms of this reaction, it lies to the right. It lies and favors the products over here on the right-hand side. Now this, of course, is opposite. You notice the Kc for this reaction right here as hydrobromic acid turns into hydrogen gas and bromine gas. I'm sorry, hydrobromide gas turns into hydrogen gas and bromide gas. What we see is that this has a very low Kc, a very small number right here, which means that this very little of this turns into these two. Most of it stays over here on this side, on the reactant side. So of course that would be just the opposite. That would be a lie to the left equation, is how it is termed in chemistry. And so let's look at one more example, sort of following this sort of logic right here. And if you take a look at this problem, we have the same one that we looked at in the last video, and this is AgCl, so this is silver chloride. It's solid, and it dissociates into an aqueous silver ion and an aqueous chlorine ion. And the Kc in this case for this reaction is 1.8 times 10 to the negative 10th. And so what does that tell you? It tells you this is a lie to the left reaction. So very little of this is going to dissolve, very little. And so what about the reverse reaction? If we're to say, okay, it doesn't go this direction very often. When we write the Kc, we are referring to the left to right motion. But if you say, okay, I'd like to express this as the opposite reaction, I'd like to express this as what happens when Ag and Cl ions come together to make the solid. Well, of course, that is going to end up being a big number. And how do you find that number? Well, the reverse reaction is always the reciprocal of the forward reaction. So if you look at the Kc for the forward reaction, it's 1.8 times 10 to the negative 10th. And so if we take the reciprocal of that, this would be over 1, so we'd flip that, and the reciprocal of it is 1 divided by 1.8 times 10 to the negative 10th. And so that would be the new Kc, or the new equilibrium constant expression for concentration of the reverse reaction of this. So this is the ions coming together, and you notice, of course, now we have a lie to the right reaction, because very little of this will be left, and it's all going to go into this. And so that should make sense as far as comparing the idea of lie to the left and lie to the right. And how do you switch between the two and get your equilibrium constant expression of one from the other? All right. Now, also in equilibrium constant expressions, we also have the idea of, oftentimes we get these equations where you look them up in the back of the book, or you see an equation that's got, you know, a half of an oxygen molecule here. Well, so what do we do with that? Because in reality, our reaction isn't going to be that. Our reaction is going to be like this. We're going to have 2 SO2 plus a single oxygen molecule, and that's going to go into 2 SO3. And so the rule is that when you take a reaction and you have to double the balanced equations, the coefficients in the balanced equations like this, the resulting Kp is the square of the previous one. So we would just take this and we would square it. So the Kp here is going to equal 1.85 squared, which equals 3.42. So if you're ever able to look up a Kp, if you look up a Kp or given a Kp like this, but you can't work with this and you need to double the entire thing, well then it's pretty simple. All you have to do is square the given Kp, and there you go. There's your new Kp, which matches up to this equation right here. And that also works for Kc as well. Now, with equilibrium constant expressions, under the heading of KEQ, so we have KEQ, we've talked about Kc, which is the equilibrium constant expression for concentrations. We've talked about Kp, which is the equilibrium constant expression for partial pressures. We've related those two. And now I want to talk about the idea of Ka and Kb. So this would be the equilibrium constant expression for an acid, but it would only be used for a weak acid, because we know that a strong acid is going to completely dissociate, and so whatever molarity you put in, you're going to end up with that molarity on the other side for your product. So we don't really need to have any sort of equilibrium constant expression for a strong acid, but in the case of a weak acid, there's going to be a significant amount of molarity of the original acid. Say for example, we have this one, and so if we look over here, we have this acetic acid, and the Ka actually is called the acid dissociation constant. That's the dissociation constant. And so likewise, the Kb is going to be the base dissociation constant. So all the rules are similar, except you notice, okay, I have a weak acid here, and so what's that going to turn into? Well, some of it is going to turn into hydrogen ions, and then my acetate molecule over here. So, or my acetate ion over here. So this KQ is actually a Ka. And so the Ka is going to equal, of course, the concentration of the hydrogen ions times the concentration of the acetate ions divided by the initial concentration, or the concentration at equilibrium of the acetic acid molecules. All right, so then also, of course, you can see how once you figure this out, you could use this, the concentration of the hydrogen ions, you could use that in order to solve for pH. And similarly, with the Kb, or the base dissociation constant, you could do the same thing. Say, for example, I have ammonia, and when ammonia combines with water, it mixes up into a reaction creating an aqueous solution of NH4 and OH negative, which of course is a base. And so then when we look at the base dissociation constant, we're able to write this products over the reactants. Now of course you don't include the water in this because the water is a pure liquid, and we know that in all of our equilibrium constant expressions we exclude pure liquids and pure solids because they don't change enough to cause any effect whatsoever. And so that's all of interpreting equilibrium constants. We have these, and there's only one more that we'll look at real quick, and that other one is what we call the Kw. And the Kw is actually the water ionization constant, and the Kw always equals 1 times 10 to the negative 14th. And all that expresses is that you have water, and so water, of course, can break up into hydrogen ions and hydroxide ions. And so at 1 times 10 to the negative 14th, we're talking about a concentration of 1 times 10 to the negative 7th for the hydrogen ion, and 1 times 10 to the negative 7th for the hydroxide ion, so therefore they're equal. And so then this would also give us a pH of 7. So the Kw for water is an expression actually of the concentrations of hydrogen ions to hydroxide ions where they're equal, and which of course would define water, because we don't have any more hydrogen ions than we do hydroxide ions, therefore they all match up to equal 1 water molecule each.